As we saw at the end of the last video, there's a lot of really good reasons to use raster data to answer specific analysis questions. There's a lot of positives, and the most fundamental one of these is that there's really fast operations and a wide number of different quantitative operations that can be used to create derived values from overlying layers, or the values of overlying layers from different data sets. So in this video and the next, I'm going to talk about important issues to consider when working with raster data. That's these first couple points on the slide. You have to set and check your environments. It's a really important step. And then kind of there's a broad topic of map algebra, or the raster calculator in ArcGIS is kind of the fundamental tool in conducting raster data analysis. And then we're also going to look at specific analysis tools. And most of these are grouped within several categories of operations that are shown in those last couple points on this slide. So there are local, neighborhood, zonal, and global operations. We'll talk about each of those. But in this video, I'm going to focus on the local operations. So how we set up an analysis when we're working with raster data, and then how we carry out that analysis using map algebra, the actual kind of mechanism with which we apply this analysis a lot of the time. And then again, we'll look at the overarching categories starting with local data analysis. So a first step in conducting raster analysis is setting the environments. It's really, really important. It's really required when working with multiple raster data sets at once, or when combining those data sets together. All these things you see in the environment pane at the right are essentially parameters that run with a tool. So remember, every time you run a tool, you set all those different parameters. But in the case of raster data analysis, there are more parameters than just what you see with the tool. And with these environment settings, you have the power to influence the output and set these kind of larger, higher level parameters that affect how the tool actually runs. So it's really important to pay attention to these things. So there are a couple key environment settings that are important to know about that can really help improve your analysis or solve problems or just kind of make your workflow a lot smoother. First, your inputs might have different extents. So if you get data from different data sources, again, these rasters are just like hundreds or thousands of rows and columns of little pixel or cells. It makes sense a lot of the time to make sure that the rasters you're going to work with are set to the same extent and are only set to look at a particular area. If you download one raster that, is the whole county or the whole US, and you're really just looking at like a stretch of coastline, then you'd want to make that have a smaller extent. So you can set this setting in the environments area. So the processing extent allows you to set what you want the boundaries of input to be. You can set it manually and just input the coordinates of each corner, or more commonly, you'd click the drop down next to extent and select the raster you already have that's the most appropriate size for the analysis that you're doing. So then another really important parameter is in the raster analysis section. It's called mask. A mask allows you to choose a specific area of analysis. Again, this can work similarly to the extent function, but you can actually select more specific masks than just kind of the extent and the four corners of a data set. Selecting a mask can allow you to select a more unique shape according to an overlying data set for your output data. I'll talk more about this in a second with a couple more visual examples that might help clarify this a little bit. Finally, it's really important to think about the cell size of the output if you have different pixel sizes going in. So again, you might have two layers. One has 60 meter cells, one has 20 meter cells. So it's a really important question that you have to ask is, what size of cell do you want your output to be? You have some power over this. However, there are kind of best practices in choosing which cell size your output should be given different input sizes. And again, I'll talk about that in a couple slides. So overall, the environments area in ArcGIS, once you click environments from the ribbon, it'll look like what you see at right. There's a couple of these key parameters. You also have things like workspace, output coordinates. You can set these as well. A lot of times these will be defined by default. Based on your project settings. So in ArcGIS Pro, you set up that project. You already have kind of default geodatabases, and these usually correspond to just that data set, the geodatabase that gets set up as part of your project when you establish the project in ArcGIS Pro. So we're going to look a little more at a couple of these environment settings. The first of which that I wanted to talk a little bit more about is mask. So this is kind of a more specific way of limiting the extent of your output, but it allows you to have a little more power over the output than that just setting what literally the extent of those four coordinates at the top left, top right, bottom left, and bottom right corners of your output are going to be. So if you just want like a square output with very specific ends to each of those corners, you can do that in extents. If you want a more refined or more particular output, you can do that with masking. So it's not the most intuitive term, so it's kind of important to clarify what it is, but if you've used clip with vector data, the result is similar. A mask is used to carry out analysis only on those cell values that correspond spatially with the mask layer. And the mask you choose can be based on another data set or a value within a data set. So for instance, you can mask by a whole administrative boundary layer, or you can mask by a certain value within that. And if you mask by a certain value, again, for nominal values like county, they're going to be coded. The output would only have values within the city, county, or national park code that you choose. So a certain county might be marked as like county 54. All of the cells in that county layer for that county will be 54, and you can mask by that value of 54. That'll give you something like what you see on the slide. So this is demonstrating the use of the mask. Here it looks like maybe we have land covers as input, and then in purple is some other value. Again, that might be something like counties. Everywhere in purple is the specific county that you want to look at, and you only want your output to correspond to that county. If we mask the input data set by the county or purple layer and run whatever analysis we're doing, this tool, running some raster or spatial analysis tool in ArcGIS, you would just get that output that's shown at right. There are only valid populated values for areas that fell within that purple area. Everywhere else has no data values because there were no data in that mask layer, or they weren't the selected value of that mask layer. So sometimes you might have a large raster data set, but you might want your output just to correspond to a smaller area within that. You don't want like to run a tool on every single cell. You only want it in a specific area. A mask is really useful for doing this. And then that note about pixel size I kind of alluded to at the beginning slide for this topic. The best practice is to use the largest pixel size of your inputs as the output pixel size. But again, this is something that you set in environments. The default will actually be that setting of having the largest pixel size as your output. So you might be wondering, like, why should that output resolution correspond to the lowest resolution input? So like, for example, on this slide, if you have 1 meter to 1 meter layers and you're combining all these together, you should use 8 meters for an output. The answer to this is basically that your results are only as accurate as your least accurate input. So if you use a small resolution as your output, then your output appears to have more accuracy than it really does. So you don't want to like mislead what your results can actually say about the real world. So if you have like an 8 meter resolution layer like this one right here that says there's maybe forest within this 8 meter by 8 meter area, you can't break that apart and say that for every 1 meter by 1 meter pixel within that 8 meter pixel that we're calling forest, you can't say with certainty that every single larger scale cell that would be 1 by 1 is actually forest. Because when you're looking at a forest pixel that's 8 meter by 8 meter, that just means that the majority of that area within that 8 by 8 area is forest. It doesn't mean that literally everywhere within that cell is forest. So later, if you conduct analysis and say that these smaller cells within that 8 meter cell are all actually forest, you're going to get errors that propagate down the line. These 1 meter cells are all going to be wrong because you basically assumed that just because something at a larger area was forest, that smaller area within it is forest as well. So this can give you even bigger problems when you're talking about things like elevation or quantitative values and you're actually conducting mathematical analysis on them. Just because a cell, maybe an 8 meter by 8 meter cell, has an elevation value of 10 meters, if you break that down into smaller cells within it, each of those cells doesn't have 10 meters within it, and if you say they do, then you're introducing significant error into your analysis. It's more accurate, though maybe less precise, to resample that finer detailed information to a larger pixel size. So instead, if you have a 1 meter resolution layer of elevation and an 8 meter layer of land cover and you want to combine them in some way, you should average that 1 meter elevation layer to create 8 meter elevation cells to combine with the land cover data. So you take all those cells of elevation, all those 1 by 1 meter cells, create an 8-meter cell that includes them, take the average value from all those smaller cells as your elevation for that layer. That's the best practice for working with different cell sizes or pixel sizes. ArcGIS tools resample automatically, so you don't usually have to conduct separate tools to carry out this resampling process, but you should, within settings, make sure that the proper setting is set, that your output resolution is what you want it to be and that it corresponds to that largest cell size. Okay, so once those basic data management considerations are out of the way, you can conduct many types of operations using raster data. These are essentially algorithms that take one or more input pixel layers or raster layers with their different cell values, and some sort of mathematical or statistical modification or algorithm will be conducted to that value, resulting in a new output raster with unique values for each pixel. Again, there are 4 different categories. We have local, focal, which are often called neighborhood. I think on my intro slide I had neighborhood, but focal and neighborhood are often used interchangeably. Zonal and global. Each of these requires a different amount of input data, and they also employ different operations in transforming that input data and getting an output layer or output data set. There are also fewer use cases as you move from left to right. So the rest of this video, I'm going to be talking about local operations. These are basically operations that take an input value, modify that value in some way, and then output another value in its place based just on the original value that was in that input cell. So a fundamental tool that's central to carrying out any of these types of raster operations is the raster calculator in ArcGIS Pro, which carries out a more general form of analysis called map algebra. So in ArcGIS, this map algebra is carried out using the raster calculator tool, and that appears as at right. In this tool, available rasters are listed in the left, and operators are listed at right. So operators indicate the operation that can be undertaken between cells in each of these rasters, or even in just one raster. Some of the tools that we're going to look at in the next few slides or the rest of this lecture can be implemented as individual tools, but you generally can run any sort of raster analysis straight from the raster calculator as well. In the lab for this week, for example, you're going to run several operations as tools that could be run directly in this raster calculator, but in the lab they're going to be run as independent tools. In the class of operations that are called local operations, you almost always employ a method that could use raster calculator based on one of the operators that's available here. All right, so at right, we have map algebra as implemented in the raster calculator in ArcGIS Pro. We have 3 input rasters, intro raster 1, 2, and 3. The first 2 rasters are added together when you look at the actual operations being carried out in the box in the kind of towards the bottom. Intro raster 1 plus intro raster 2 times intro raster 3. What's really happening is that the values of each of those overlying cells are being modified. So a cell that corresponds in space between these 3 rasters will be added together between those first 2 rasters and then multiplied with the 3rd raster. So again, according to order of operations, I guess the multiplication will occur first, and then the addition will occur after that. So we'll get intro raster 2 times 3 plus intro raster 1. That'll be output as raster 1. So these local operations that you carry out using raster calculator or via specific tools are categorized or known as cell-by-cell operations. They're operations that work within a single cell. They use some operation or operator, according to the raster calculator on the last slide, to transform the value of a raster cell into a different output value. The really important part here is that the input and output cells correspond to each other in space. There's a direct link applied between the input and the output. And what you get as a result is the creation of a new raster from one or more input rasters. The location of the cells will be the same. The value will have changed in some way. So let's look at a few of the more specific ways that you can actually modify those original cell values to get some different output value. All right, so here's a really simple example, and this is a local operation that's carried out all the time, all over the world in GIS by pretty much everyone that's ever used GIS. In this case, we're looking at a local operation that only needs one input raster, but again, that input raster is modified in some way and output into a new raster with new data values. In this case, we're doing this local operation on a digital elevation model. If you look at a DEM at right, and then you zoom in really far and query these different cells, you'll see that the elevation for each of these cells is coded into the cell itself. They have an elevation in meters in this case. Each of these little squares has a meter, a value in meters. It's coded as a floating point value, so that at the top left we have 117.09 meters. At the bottom right we have a lower value of 74.91 meters. It looks like this is somewhere along a river basin, so we have a pretty quick change in elevation. And what we want to do here is change this DEM from meters, how they're usually supplied, to feet, which can be useful for local analysis in the US. If you're looking at doing some planning in the US, a lot of people use feet. So if we have this DEM and want it in feet, all we have to do is carry out a very simple local operation that can be carried out in that raster calculator. So what would we do with each of these cells to get feet? We'd simply multiply them all by the conversion, or apply some conversion factor. In this case, it's multiplication. Just very simple map algebra. For that 117.09 meters in the top left, if I asked you to convert that by feet and told you there's about 3 feet in a meter, you just basically multiply 117 by 3, right? So in Raster Calculator, by carrying out map algebra, we can basically do this command for all the cells in this entire raster, and that's what we're going to do. So we know that 1 meter equals 3.28 feet. It's a little more precise than that last value I gave you of about 3. We just know that we want to multiply each cell by 3.28 to get an entire raster that's in feet instead of meters. So what the raster calculator basically does when you enter this equation into it is it essentially starts at cell 1, remember that's in the top left, and it multiplies the value of that cell by that conversion factor, which is 3.28 in this case. So in this case, the output cell for that raster will have 384.06 in that cell instead of 117.9. It's simply just multiplying that cell by the conversion, which is 3.28. Then it'll go to the next empty cell in the output raster, multiply that one by the same 3.28. In that case, we'd get 362.18. All of the overlying cells are filled this way in the output raster, and you'd end up with an entire raster that's in feet instead of meters as an output. All right, so the last slide kind of showed essentially what the computer's doing behind the scenes, but this is all you have to do to implement this in ArcGIS. This local operation implemented via Raster Calculator, you basically just say raster times 3.28. You put in the raster's name there, and you put in multiplied by 3.28. Because all of these cells, all they have is the elevation value in meters, all you have to do is say that for each of those you want to multiply them by the conversion factor, which is 3.28. You would end up with this new raster layer that's in feet, named whatever you call it in the output raster box. So there are a few more specific examples of these operations that you'd want to carry out cell by cell as a local analysis method using raster data. So instead of just multiplying one value and getting that output value, that's the multiplied input value, you can do a few slightly more complicated things. You can apply a power function. So in the example on the top of this slide, we have each of these cells, cell by cell, basically squared. So if you take 1 squared, it's still 1. At the bottom left, if you take 4 squared, the output would be 16 instead of 4. Again, 0 squared is 0. So you end up with a new range of values based on just squaring the original value in each cell. You can also round down as another example. So in this case at left, we have all these values with decimals, 1.3, 1.2, 2.5, 0.1. But if you only really want whole numbers, you can just round those down. This might be useful in later changing the data type to an integer rather than a floating point value. So if you just want to simplify things and only store one value in each of these cells instead of a couple values with decimal points after them, you can round down and then convert. So one really useful tool that's usually implemented as a separate tool in ArcGIS, it actually has its own tool. It's a little more challenging to do in the raster calculator, though it's possible, is reclassification. This is still single raster local data analysis. But what basically happens is you get a new raster that's derived from a classification of the original raster values. So it means you take all these original cell values and group them according to some pattern that you decide on. Usually it's used to assign a new range of values to a larger range of values. So at right, we have elevations ranging from 5 to 500. That might be kind of more detail than we actually want. We might want to simplify things for further analysis. We might just want to know whether something is high, not so high, medium, or low. That might be easier for whatever analysis we're doing. It might be easier to compare with other data we have. So for instance, you might be combining elevation with land cover. It'd get overly complicated if you combine elevation and land cover and have an output coding system that has cells that say like forest that's 456 meters, forest that's 416 meters. For analysis purposes, that wouldn't really be helpful. What would be a lot more helpful is having high elevation forest, medium elevation forest, and low elevation forest. That's a sufficient number of categories to be meaningful, but it's not too many that it's just kind of overwhelming in the number of categories. It's a meaningful number of categories. So to carry out reclassification, you have to decide on the number of classes and the class ranges. In this case, we want 5 classes, again ranging from high to low, with kind of a middle value at 3. And by looking at the entire range of values from 5 to 456, you might decide that a reasonable range for each class would be 100 meters. So in designing this reclassification, you'd say from 0 to 100, we're going to say that's a 1, 100 to 200, that'll be a 2, 200 to 300, that'll be a 3, 300 to 400, that'll be a 4, 400 to 500, that'll be a 5. Once you enter these into the reclassification tool and run it on this input raster, you'll get a vastly simplified reclassified raster or output raster. So now, instead of having a whole bunch of unique values, we have 5 different groups of values. So every cell is basically coded whether it's low, slightly low, medium, medium high, or high. This is much simpler and much easier to combine with other nominal data, again, something like land cover. And this is something that you'll do a lot with raster data, and it's part of this week's lab as well. All right, so far we've talked about local operations that are carried out with just one input to modify the value of an input raster, get an output raster just based on the value of that single input. But a lot of the time, when you're doing map algebra, you're going to be actually using local operations with multiple rasters. There's a huge array of functions that can be used to combine 2 or more rasters. This example right here is simply an addition of 2 rasters to get an output raster that for each cell has the sum value or added together value of the cells in each raster that overlie one another. But there are many other operations and functions that can be used, and we're going to look at some of these on the next slide. Some are used really frequently, and some are like really kind of unique use cases that are a little less intuitive, that might require a little bit thought to think about like when or why you might use one of these. But we'll start with the straightforward ones. All right, so here are these basic operators that can be used in a raster calculation, combining 2 different raster layers. These basic operators are things that are placed between 2 inputs to carry out an operation. So usually when you're using these basic operators with raster calculator, you're going to have 2 cell values as inputs, and you need to define a relationship between them. And these basic operators include basic arithmetic, which means adding them together, subtracting them, multiplying them, dividing them, looking at the absolute value of these layers. You can also square them or do some other power beyond square, or take the square root of them, or you can conduct some statistical analysis among them as well. Imagine you have 10 different rasters for air pollution for the same location, and you just want to know among those 10 rasters, you want an output raster of all the highest cell values for each location. You could just put them all in raster calculator, all 10 of these, and say, I want the statistic of maximum from these different dates to be the output, and you'd get that. You could also take the mean if you're just looking at average values over time. So if you have 10 days of data from the same location and you just want to average those to see what the average is over a long period of time, you could combine them in raster calculator, all the values for that cell in that location. The mean would be calculated for each of those and output in that output raster. All right, so a really simple example of one of these basic operations using a basic arithmetic operator is, again, just adding two rasters together. In the top left cell, we have 4. That added with a no data cell just results in 4. If we look at the bottom right, the first raster has a value of 4 at the bottom right. Second raster has a value of 10. The output value would be 14 for that raster. That's your output. Another really important local analysis method that basically combines different categorical or nominal raster layers is simply called the combine tool. So this is just another raster analysis tool that as input takes 2 rasters representing categories. So that means that each of these cells is coded according to membership in some category. And then the output gives a new value for each combination. So in this example in the slide, we have 2 input rasters. Each of these is a coded value for something. So at right, we have values 0, 1, 2, and 4. Those are coded to phenomenon 2, 4, 5, and 8. We don't actually know what they are. That could stand for, again, different zip codes, different counties, things like that. In raster 2, we have 4 different values that still are nominal. They're defined as type pax, har, win, or san. Again, not really sure what those actually mean. But when we run a combine operation, the output will give us every combination of values from 1 and 2, and each of those combinations will get a separate output value. So in the output data set, we have a value for all of those inputs that for in raster 1, the value is 1, in raster 2, the value is 2, in raster 1, the value is 1, in raster 2, the value is also 1, all the way down to when in raster 1 was a 4 and in raster 2 was a 3. So that happens in the bottom left of those in rasters, but it's coded as an 8 in the output data set. So this basically gives you every unique combination of 2 raster values when you're looking at 2 or more different data sets. So this gets out of hand really quickly if you have a whole bunch of categories. It makes sense in the case like on this slide where the 2 input rasters, there are 4 different categories. As an output, you get something like 9 values. If there's a combination that doesn't exist, it's not included in this output. So for instance, there's no case where the in raster 1 has a value of 4 and in raster 2 has a value of 2. That doesn't look like it exists. So it's just not included. So there could be even more values given this combination if those values existed, if this was like a real larger raster. Another good example of a use case of this would be looking at something like land cover and soil type. These are 2 nominal categorical variables that are often represented by raster data. The output would be each unique combination of land cover and soil type. All right, there's one more big group of these local operations, and this consists of logical and Boolean operators. These get a little more complicated, and they're also things that aren't used very often. They're a little less intuitive. But basically, they compare input rasters and output binary results if certain conditions are fulfilled. So if you just quickly look at the out raster for each of these examples, the output for any of these is just going to be a 0, a 1, or no data. Logical operators include greater than, equal to, not equal to, whereas Boolean operators include those cases where non-zero is true, 0 is false. So it's basically comparing some condition and saying if that condition is true or false. If the condition is true between those 2 rasters, the output will be a 1. If the condition is false, the output will be a 0. So looking at the 2 examples on the slide, we are asking in the first one, the logical operator example, if raster 1 is equal to raster 2. If for a given overlying cell, the raster values are the same, the output will be a value of 1, saying yes, they're the same, there hasn't been a change, or there's no difference between them. If there is a difference and there has been a change, the output will be 0 in this case. So we only have 3 cells where they are equal between input and output. All of those happen to be the input locations where we have the value of 2. So using this constant raster as your second raster, where every value is 2, means this basically functions to just check for locations where there's a value of 2. So you can do this via a local operation like this, instead of just kind of maybe symbolizing your layer by only showing that the locations are 2. So if you want an actual output raster that says all those locations where the value is 2, you'll actually end up checking the two rasters with this logical operator and getting an output that says, yes, these values stayed as 2. Boolean, again, is a little bit more abstract, but when you're using, for instance, the AND Boolean operator, you get a binary output where both cells contain values. So in this case, you're looking for 0 as the input is not true or false. Any valid input is true. So this is basically essentially checking for just anywhere that has a value versus places that have a value of 0 or no data. So for each of these in rasters where there's a value that's above 0 in the same location in each of those rasters, the output will have a 1 in that location. If one of them has a value that's above 0, one of them has a value that's 0, you get an output of false. And if you have a no data value, you'll get an output as a no data value as well. These Boolean operators aren't clearly tied to any specific type of analysis, but they can be pretty useful for data processing and for intermediate analysis. So for instance, imagine you have something like hourly data on air quality, and you want to know which areas got better or worse. You could subtract each of these time periods to end up with areas above 0 and below 0, but you might just want a simple yes or no output. And you can use the logical operator to get that yes or no output. Is it increased from what it was before, yes or no? For Boolean operators, like the example at the bottom of the slide, you might just want to use that to double check for areas that have data at all time points. You could get load in a bunch of input layers for, again, something like air quality. And by using a Boolean operator, you can just get all of those cells that over that entire range of data have valid data for that cell. If one of those cells in the input raster has no data or has a 0, which you wouldn't expect, that will result in an erroneous output pixel or a no data cell for that location. You can later use that layer as a mask for further data analysis. So you don't get error values when conducting further analysis and combining it with other layers. All right, so just to finish out this video, I have a couple examples of using local operations for pretty complex things for really meaningful, important analysis. So many types of environmental change maps are simply just using local operations. These are maps of land surface temperature. So we have time 1 and time 2, 2 different years, same month, and we have the average temperature of land surface features. So how hot are features on the surface of the Earth? They really kind of look the same for these 2 years of input data, both, again, just pixel cells or raster cells indicating what the temperature is. The total range is the same from -25 to 45, and the general pattern from south to north looks pretty similar. But we can carry out one of these really simple local analysis methods and just find the difference between them by subtracting one from the other to get a map of change instead of just trying to compare these two maps manually. All right, so when we get that map of change, if you subtract 2014 from 2015, you get a map like you see it right. This is simply done pixel by pixel through something like Raster Calculator. You end up with positive values where places have become hotter, so a higher change value of up to 26.1, and there are low negative values in blue, so there are clearly areas that pop out as increase or decrease in the temperature in those areas. Then finally, this is one that's really complicated when you break it down into individual pieces, but as an overarching example, it's a really good example of local raster analysis being used for really complex environmental analysis. So this one's used in geography quite frequently, and in environmental modeling, it's called the Revised Universal Soil Loss Equation. And it's a model that provides an estimate of the amount of erosion in a place based on a whole bunch of environmental input factors. Each of these factors is spatially explicit and brought into the equation as a raster data set where there's a value for each cell. So there's a value or score for each location, for each constituent part of this equation. One of these parts of the equation is shown here. This is the R factor, which is basically how much rainfall relates to erosivity in an area. So areas with high rainfall can cause more erosion, and this is input as a raster data set where each cell has a value for the erosivity factor. So first, the local operation converts raw rainfall into the effect of that rainfall on erosion. That's the transition shown here, where we have average annual rainfall at left and the modified value of rainfall erosivity at right. Then that image is just one of these main inputs to the equation as a whole, where that's the equation shown at the top, where A equals RKLSCP. So rainfall erosivity is the R of that equation. So that R value, which is shown on the slide, is simply multiplied pixel by pixel with all of these other factors at right. Things like soil erodibility, topographic factor, the type of crops that exist in a place, and whatever conservation practices exist in a place. They're simply multiplied together to get a cell value at each location for average annual soil loss in that location. So basically, these were some pretty simple operations that can be really powerful when combined in certain ways in modeling tools like this RUSLE.